Welcome. In this video, we're going to be looking at maximum likelihood estimation for the p parameter of the binomial distribution. So to begin with, suppose we have a sequence or sequence of independent and identically distributed random variables, which we'll call x1, x2, all the way up to xn, and we're going to say that they're distributed binomially with binomial parameters m and p. And further to this, we're going to assume where m is known. In other words, we know how many trials are being conducted, but we want to work out, or we want to estimate the value of p. So if this is the case, now I want to point out, usually you'll often see a binomial distribution parameterized by the quantities n and p, but in this case we're going to use m, and the reason I do that is to distinguish between this parameter here and the number of observations, or the number of random variables under question. So if we do have a binomial distribution with this parameterization, the probability mass function of xi, of any of the xi's, is given by, well, let's write it out. So we've got p xi given m and p is equal to, well, it's m xi, m choose xi, p to the xi, 1 minus p to the m minus xi. And of course this is true for xi, any xi in between 0, 1, 2, all the way up to m. So using this probability mass function, we can work out the likelihood function is, well, the likelihood function from our memory, and now again our likelihood function is only in terms of what we want to estimate, and in this case we only want to estimate p, so it's L of p is equal to the product I equals 1 to n of p xi given m p. And again, so that is the product of all the respective marginal distributions, or marginal PMFs, I should say, of the xi's, the product. So in other words, and then that product here is gives us the joint PMF of x1, x2 up to xn. But that is also equivalent to the likelihood function. So again, doing a bit more simplification here, or first actually writing in an expression, or writing this expression, or replacing it with the expression above actually. Here we get m xi p to the xi 1 minus p to the m minus xi. Going to do a further simplification here. What I'm going to do is I'm going to split it up, so that's I equals 1 to n of m xi. That's the first part. Then I'm going to split it again up into the product of I equals 1 to n of the p xi's. And finally I'm going to have one more part, which is I equals 1 to n of 1 minus p to the m minus xi's here. So this this particular expression here is not going to change. That's just going to be I equals 1 to n mxi. Now this expression here will change a bit. So we're going to use the power laws. So here the product of p of a base all to different powers can actually be written as p to the sum of all those powers. And likewise, that can be done here. So you've got 1 minus p, all the same base. The powers change, so that becomes 1 minus p to the sum of the powers, I equals 1 to n m minus xi. Now we're almost done. I'm just going to do one more bit of simplification. This stays the same, m xi. This stays the same, I equals 1 to n xi. However, in this particular expression here, what I want us to notice is that here we're summing m, that m at the front, n times. So instead I can just say that's n times m minus the sum I equals 1 to n xi. And from here we have derived an expression for the likelihood function. Of course, now we have to find the log likelihood function, so the log likelihood function is given by, well, what's the log likelihood function? Remember, by definition, the log likelihood function, which I give the lowercase l, is equal to log L of p, where L of p is the likelihood function. Then I'm going to substitute in our expression that I wrote above. So I'm going to take that, copy that, paste that down here nicely. And so now it becomes a little bit interesting, because the first step here when we deal with logs is, remember, the log of a multiple, or log of a product is the sum of logs, so that this becomes log of I equals 1 to n m xi here. So that's our first expression, plus log, again here this becomes p to the sum I equals 1 to n xi's, and then our final term here is log 1 minus p to the power of n m minus I equals 1 to n xi. Alright, looking good so far. However, I'm going to do one further simplification step here. So I'm going to leave this part here actually as I equals 1 to n m xi. That part's not really bothering me. But this part I'm going to rewrite. Remember, when we have a power in the logarithm, or the logarithm, we can take that power down the front. So that would be bringing that power down the front, I equals 1 to n xi, except, and then we'd be left with log p. So I'm actually just going to put log p out the front, just so it looks a bit nicer. And I'll put this in brackets here. Plus, and again we're going to do the same thing here. We've got our power that's coming down the front, log 1 minus p, and then we've got our power n m minus the sum I equals 1 to n of xi. And so now we've found an expression for the log likelihood function. So now what we're going to do is we're going to differentiate this expression and then solve it equaling 0, and then we're going to differentiate it again, and we're going to use the second derivative test to show that it is in fact a maximum. So let's do that now. Differentiating with respect to p gives, well, this one might be, so we're going to differentiate the log likelihood function with respect to p. So here there are no terms involving p, so actually that's not a problem for us. This just goes away because it's a constant in terms of p. This is a constant in terms of p, but we're multiplying by log p, so that becomes the derivative of log is 1 over p. I equals 1 to n xi here. And equally, this is a constant in terms of p, but we've got to differentiate log 1 minus p. So the first thing we know is that 1 over log becomes 1 over p. Then we've still got our constant here, I equals 1 to n xi. However, we don't want to forget that there is a negative inside the log, or there's a negative 1 as the coefficient of p, so we have to take the derivative of the inner function, which is negative 1, so it becomes minus there at the front. Okay, wonderful, we've done that. So now we're going to find actually the second derivative now. We might as well. dp squared is equal to, now the derivative of 1 over p becomes minus 1 over p squared, I should say. I equals 1 to n xi. And the derivative of 1 minus p, remember actually that this expression here is 1 minus p to the negative 1. So the first thing we have to do is bring the negative 1 down the front. That'll get rid of the negative. Actually, what I'll make sure there's a negative here. So the first thing we're going to do is bring the negative 1 down the front, which will get rid of the negative at the front. Then this becomes a negative 2, of course, because you take 1 off the power. But then we've also got to differentiate the inner function, which just becomes negative 1. So we actually still end up with a negative at the front. And so altogether, that becomes 1 over 1 minus p squared, because of that negative 2, nm minus the sum of I equals 1 to n xi. Now, so we've differentiated, and now, twice, now we've got to find the MLE. So, to find the MLE, or the maximum likelihood estimate of P, which we label P hat, we solve the following equation. dLP over dP evaluated at the maximum likelihood estimate is equal to 0. So I'm just going to copy and paste, or copy this particular expression here that we have. Now that is in terms of P, so we have to write hats here wherever we see a P. So we've got to solve this equaling 0, and the first thing I'm going to do to solve this particular problem is I'm going to take this expression here and move it to the other side so that they're both positive, or in other words, 1 minus p hat nm minus I equals 1 to n of xi is equal to 1 over p hat, the sum of I equals 1 to n xi. And now what we can do from this particular scenario here is I'm going to do something a little bit tricky, and you'll see why it's tricky in a second. What I'm going to do is I'm going to try and get all the p's on one side. So this 1 minus p I'm going to bring to this side, and I'm going to take this sum of xi and I'm going to divide it onto this side. So the next step in this equation becomes nm minus the sum of xi's all over the sum of xi's is equal to 1 minus p hat over p hat. And we're almost there. What we're going to notice now is that I'm going to actually do some simplification, and then this becomes nm over the sum of I equals 1 to n xi, and that's that first bit of the fraction. Now I'm going to concentrate on the second bit of the fraction, so that's the sum of xi's divided by the sum of xi's, which is just simply 1 or minus 1. And I'm going to do the same here. The first part of this fraction here is 1 over p hat. That just becomes 1 over p hat. And then we've got minus 1 p, or minus p hat over p hat, which just becomes minus 1. And now you're beginning to see we're almost at the point of finding a value of p hat here. You'll notice this minus 1 will cancel away with that minus 1, or they'll take away each other. So 1 over p hat is nm over x, the sum of xi's. So that means that p hat has to be 1 over nm times the sum of xi's. Now if you want, we can do one further simplification, which is actually xn bar over m. So remembering that xn bar is the sum of xi's divided by 1 on n. And we've still got the 1 on m here. And so hopefully this will be our maximum likelihood estimate. However, to prove that the likelihood function is maximized by this expression we've just found, p is equal to p hat, which in this case we've said is xn bar over m, we must show, all we have to show is in fact that the second derivative of the log likelihood function evaluated at the maximum likelihood estimate is less than 0. And if we can show that, then we have shown that this is in fact the MLE and that the function is maximized at that point. Now to do that, just note, so I'm going to, now let's actually try and find our expression for the second derivative. So here it is here. Copy that. And I'm going to paste it here for us. So here's the expression. Now, what I'm going to do with this expression very subtly is I'm going to take this negative, I'm going to take this negative here, and I'm going to take it out as a common factor. So I'm going to put that as a plus, and then I'm going to just put brackets around everything here. And what I'm going to show to you is in fact that this expression here is less than 0 for all values of p. No matter what the value of p that we have, it's going to be less than 0. And to show that, I'm going to do it in steps. So this first expression here, 1 over p squared, well, that has to be p squared is greater than 0, so 1 over p squared greater than 0. The sum of xi's, remember xi's are observations from a binomial distribution, so their sum can only at least be greater than or equal to 0. I mean, theoretically, they could all be 0, but for this case, I'll leave it like that. Now, the sum of, or 1 over 1 minus p squared, again, is greater than 0. And here, the only thing we have to note is that this expression here, the sum of xi's, at best, all our xi's could be, at best, they could all be a maximum of m. So this expression, this sum of xi's, has at best a value of, or at maximum a value of m times n, which means this expression here at minimum, n minus n times times m minus times n times m minus m times n, together this whole expression has to be at least greater than or equal to 0. And so putting that all together, everything here has to be at least greater than or equal to 0. And we've got a negative in front, so we've got the sums of things and products of things that are all greater than 0. We've got a minus here, therefore it has to be altogether less than 0, irrespective of the value of p. So because it's irrespective of the value of p, we know it's true for all values of p, then we've proven that definitely at p hat that this is also true. And so in conclusion, the MLE of p is p hat, which is equal to, in this case, x bar n over m. And in this case, I've chosen to use a capital letter as opposed to the lowercase. And that concludes this video for finding the maximum likelihood estimate for the p parameter of the binomial distribution.